Hello everyone, I am Haifeng Sun from Peking University. Today it's my pleasure here to present our paper. In this paper, we focus on the stream-based network telemetry. This works abstract the network traffic into the packet stream, in which each packet is a key-value pair. Since the programmable switches are equipped with great in-network visibility and high performance, there have been numerous telemetry solutions built atop them, such as sketch-based algorithms, intent-based measurement systems, and so on. They collect various flow statistics of interest in the data plan. Note that the packet stream is unbounded, which is unrealistic to process entirely. Therefore, all the telemetry solutions rely on the window mechanism to split the packet stream into continuous windows. Each window has faint packets. I use the counting sketch as an example to illustrate the workflow of the window mechanism in the data plan. In the first window, the counting sketch records the number of packets for each flow. When the first window is over, the switch OS collects the measurement state and then resets the counting sketch to process the packets of the next window. Here, the time of collection and reset is significant to the measurement accuracy. If the C and R time usage is too long, the counting sketch cannot process the packets of the next window in time. As shown in the figure, we use tumbling window and the sliding window to perform anomaly detection respectively. The tumbling windows are easy to ignore anomalies around the boundaries of two windows. However, due to the limited hardware resources and the programmability of commodity programmable switches, existing telemetry solutions only support fixed-size tumbling window. This motivates us to design a general window mechanism framework, which can support both arbitrary window size and arbitrary window type. To achieve our design goals, we summarize the switch constraints on the window mechanism. D1, the switch OS-based C and R operations incur high latency. D2, common clock synchronization protocols among switches, such as PTP, are significantly influenced by the network workloads. Thus, for a network-wide telemetry, packets are easy to be monitored into different windows on different switches due to the deviation of their local clocks. Both the constraints degrade the measurement accuracy. D3, the memory and the computing resources of commodity switch ASICs are scarce. As a result, we cannot allocate enough resources for telemetry solutions to realize large window size. C4, current programmable switches adopt the single-pass pipeline architecture with strict memory access model, while sliding window needs to process a packet multiple times. That is, sliding window repeatedly process one packet in multiple windows. Therefore, if we build a sliding window in the data plan, it requires multiple tumbling windows in one pipeline to process packets separately, whose resource overhead is unacceptable. To this end, we propose OmniWindow, a general and efficient window mechanism framework. Its key idea is to split the window into fine-grained sub-windows and merge the sub-windows into the complete window as needed. OmniWindow takes a collaborative architecture, while the data plan monitors the packet stream in the granularity of sub-windows, and the control plane is responsible for the merging operations. For example, here we have 6 measured sub-windows of 100 milliseconds. We can merge them into 4 continuous sliding windows of 300 milliseconds, whose slide size is 100 milliseconds. We can also merge them into 3 continuous tumbling windows of 200 milliseconds. In this way, our goals of arbitrary window size and arbitrary window type are both achieved. However, the switch constraints raise more challenges for sub-windows. For C1, sub-windows impose a more strict time budget for CNR operations. For C2, sub-windows incur more frequent window synchronization. For C3 and C4, sub-windows require higher resource overhead. To address the strict time budget for CNR operations, we propose the application-derived flow record abstraction for collection and merging. We collect AFRs via the DPDK, bypassing the switch OS and the Linux kernel of the controller. After collection, the data plan performs in switch reset, which also bypasses the switch OS. We use SIMD, that is, single instruction multiple data, to optimize the merging operations. To support more fine-grained sub-windows, we also provide an RDMA-based collection and aggregation optimization. To address the synchronization issue of sub-windows, OmniWindow proposes a lightweight consistency model, which provides two guarantees. First, each packet is always monitored at the same sub-window during its transmission, even under low network delay. Second, window moving signals are quickly propagated in the network. Here, OmniWindow supports rich window moving signals, including timeout, counter, session, and user-defined signals. Our consistency model is lightweight because it only requires in-switch operations without any extra messages. To address the resource overhead, we only maintain two sub-windows in the data plane. As shown in the figure, when one sub-window is under monitoring, we can simultaneously collect and reset the other sub-window. We further use a flattened memory layout so that the two sub-windows can share stateful errors. Please refer to our paper for more details. In our evaluation, we use two servers connected to a Tofino switch as our testbed. We use sub-windows of 100 milliseconds to realize tumbling windows and sliding windows of 500 milliseconds. We integrate OmniWindow with Sonata, a query-driven network telemetry, to evaluate 7 queries under 6 window settings. Here, we first compare ITW and ISW, which are ideal tumbling window and sliding window implementations. As shown in the figure, tumbling window is easy to miss anomalies at window boundaries. Then, by comparing TW1 and TW2, we can see that the completion time of CNR operations has a significant impact on the measurement accuracy. These two results demonstrate our motivation. Next, we compare the accuracy of our OmniWindow with ideal windows. We can see that the accuracy of OmniWindow is very close to the ideal implementations. For the tumbling window, the record difference is only 2% and the precision difference is only 3%. For the sliding window, the differences for the record and the precision are 2.8% and 4.1%. We provide more results in our paper. In conclusion, OmniWindow is the first window mechanism framework that supports sliding window in the data plane, which ensures fast and precise CNR, consistency, and resource efficiency. We built a prototype using DPDK, RDMA, and T4. The source code of OmniWindow is now available on the GitHub. Thank you.